Hello friends, welcome you all. In last lecture, we are discussed the various assumptions made in the limit state of collapse in flexure. Okay, and then we are discussed the stress strain block diagram for singly reinforced section. Now, in this lecture, we are going to discuss the design parameters and constants. Okay, so let us see first. Okay, firstly, we are calculate the total compressive forces which are act on above the neutral axis in singly reinforced section, which is represented by letter Cu. Okay, so this we are calculated by Cu is equal to 0.36 FCK XU into B. Okay, here we know the FCK is the characteristic compressive strength of concrete, XU is the neutral axis distance, and B is the width of that section. Okay. Next is the total tensile forces, that is Tu, which is act below the neutral axis. Okay, at reinforcement where we are providing. Okay, so this Tu is equal to 0.87 Fy into AST. Okay, this Fy is the yield stress of that steel, and the AST is the area of that reinforcement bar. Okay, so from this we can calculate the actual neutral axis distance, that is XU. So this neutral axis XU is calculated by using the formula 0.87 Fy into AST divided by 0.36 FCK into B. Okay, these all terms we are known. So after putting the values in these all terms, we get the value of neutral axis, that is value of actual length or actual distance of neutral axis. Okay, so with some limiting or maximum value we can say for XU max or PT limit or MU limit. Here you can see if grade of steel is Fe250, that is mild steel, then the maximum or limiting XU, that is limiting neutral axis distance, is 0.53 D. Okay, D is the depth of that section, that is effective depth of that section. Okay, then PT limit, okay, percentage of steel is 0.088 FCK, where FCK is characteristic compressive strength. From this formula, we get the percentage limit for Fe250. Then moment of resistance, that is MU limit for this Fe250 is 0.149 FCK into BD square. Okay, where this 0.149 you can call as a Q max. Okay, it is a constant value. Okay, so FCK is characteristic compressive strength, B is the width of that section, and D is the effective depth of that section. Similar ways for taut steel, that is Fe415 and Fe500. For Fe415, XU max is 0.48 D, PT limit is 0.048 FCK, and MU limit is 0.138 FCK BD square. Then for Fe500, XU max value, that is limiting XU is equal to 0.46 D, then PT limit is 0.038 FCK, and MU limit is 0.133 FCK BD square. This table is very important. Okay, so we have to consider these all values for the designing the section of singly reinforced section. Okay, so next point is the types of section. Okay, from this percentage of steel or the neutral axis distances, okay, that is XU max and actual XU, we can define the sections, that is balance section, under reinforced section, and over reinforced section. Okay, here you can see the one section that is which having the width is B and total depth is capital D, and effective depth is from top fiber to the say distance of this center of this reinforcement. Okay, that is small d. So how we can define these sections? That is first under reinforced section. So this under reinforced section we can define as when XU is less than XU max. Okay, now here XU max is what? It is the distance of top fiber to the neutral axis. Okay, that is XU max, and XU is what? It is the actual distance of neutral axis from that section. Okay, so if this XU, which are calculated by using the formula 0.87 Fy into AST divided by 0.36 FCK into B, from this formula we get this XU And XU max how we get? If the uh, steel grade is Fe250, then this XU max is 0.53D. Okay, if this value of XU is less than this XU max or the PT percentage of steel, okay, actual percentage of steel is less than percentage limit, then the section we can call as under reinforced section. Okay, so how we can calculate the moment of resistance or ultimate moment? Okay, so the mu is equal to total tensile uh, stresses into the lever arm, that is Z. So how we calculate it? Mu is equal to Tu is 0.87 F into AST. We are already seen in last slide. Okay, and this Z is the distance of D, that is effective depth minus 0.42 XU. Okay, so the formula of moment of resistance for under reinforced section is mu is equal to 0.87 Fy AST in bracket D minus 0.42 XU. Okay, here you can see this is the under reinforced section. This XU, okay, our actual XU is here, okay, and the XU max is this total distance. So this XU is less than this XU max, so we can write this as a under reinforced section. Okay, similar way, if this XU is greater than this XU max, okay, this distance is XU max and this is the actual XU. If this XU is greater than XU max, then we can call it as over reinforced section. And if XU is equal to XU max, okay, that is both the value of neutral axis is same, then we can call it as balance section. So next is suppose balance section, that is when XU is equal to XU max or PT is equal to, that is actual percentage of steel is equal to PT limit. So the section we are calling as balance section. That is mu is equal to, we can calculate mu is equal to Q max into FCK into BD square. Okay. So this value of Q max for different grades of steel, we can write Fe250 is equal to this Q max is equal to 0.149. For Fe415 it is 0.138 and for Fe500 Q max is equal to 0.133. Suppose we are taking the grade of steel is Fe415, then this formula is mu is equal to 0.138 FCK BD square. Okay, for balance section. And next is the over reinforced section. When XU is greater than XU max or PT is greater than PT limit, the section is called as over reinforced section. And the moment of resistance formula calculated by the using the formula total compressive forces multiplied by the lever arm. So this total compressive forces is what? 0.36 FK into B into XU in bracket. This lever arm is D minus 0.42 XU. So the total formula is mu is equal to 0.36 FCK into B into XU in bracket D minus 0.42 XU. Okay, this is over reinforced section. But the over reinforced sections are disallowed in limit state method. So why we are avoided this limit over reinforced section? Because in over reinforced section percentage of steel is more, okay, so than that critical percentage. Due to this the concrete crushes and reaches its ultimate stress before steel reaches its yield point. Okay, so in this case the beam will fail initially due to the overstress in the concrete and suddenly without giving any warning. Okay, so by way of large deformation and cracks, as it does in case of under reinforced section. So there a huge loss of life and property, means this over reinforced section are failed suddenly without giving the any warning before failure. Okay, and also the moment of resistance of the section does not increase the more than that of balance section, even if the steel is increased as compared to that of balance section. So that's why we are avoiding, or this is the reason why due to which we are avoiding these over reinforced sections. So hope you will understand today's session.